Welcome to Physics in Films. Armageddon, saving Earth the Hollywood way and failing. If this is your first time visiting this channel, the videos in the Physics in Film series are motivated by the work of the Hollywood directors. Each video is dedicated to a Fermi problem based on the scientific plot, or part of the plot, shown in one of the blockbuster Hollywood movies. Today's cinematographic Fermi Problem will be based on the 1998 movie Armageddon. In the movie, a large asteroid is in collision course with Earth. NASA decides to send a team of drillers on the asteroid whose task is to drill a hole on the asteroid, place a nuclear bomb in it, and finally detonate the bomb. After the detonation, the asteroid splits in two fragments which miss Earth. How good is NASA's plan? Before we even dive into the Fermi Problem, I feel obligated to make some comments about the writer's plot. My motivation for this is Hollywood's general attitude, which tends to minimize the importance of scientists and the well-being of our society and promote the arbitrary and unfounded position that any random, untrained and uneducated person is always better option than scientists to have the job done. By watching the movie, we indoctrinated that it is impossible to train existing astronauts to drill a hole. Instead, it is easier and more desirable to select a handful of drillers and train them as astronauts in just 12 days for the most dangerous task, while they also have some time to socialize during the period of the training. And when things go bad in very unfamiliar situations and unfamiliar environments, it is them who demonstrate the stronger determination, dedication, and morale to resolve the problems. Among the drillers, there is an individual who is supposed to be a genius. We are told that he graduated young from MIT, but became a driller for the money. However, the movie portrays him as the dumbest person of the group who does all the embarrassing things and makes all the idiotic statements to draw laughter from the audience. This is not artistic freedom anymore. Unintentionally, the studio has created a direct assault on science and an offense to the real astronauts. And the sad fact is that this film is not an isolated example. Universities train thousands of people. However, Hollywood movies are viewed by hundreds of millions, if not billions, of people. Creating misinformed scientific stereotypes weakens severely the people's trust to science and strengthen pseudoscientific claims. Hollywood studios must apply better critical thinking when reading a proposed script and before they approve it. Here is what it takes to be an astronaut, a true hero. The following information is extracted from NASA's public documents. To become an astronaut is a long and arduous process. It includes multiple steps. A. The basic selection process. B. The advanced selection process. C. The basic training. D. The formal training, and E. Additional specific training as necessary. The basic selection process screens applications for ensuring the minimum requirements. These are a bachelor's degree from an accredited institution in engineering, biological science, physical science, or mathematics. Quality of academic preparation is important. Degree must be followed by at least 3 years of related, progressively responsible, professional experience, or at least 1,000 hours of pilot and command time in jet aircraft. An advanced degree is desirable and may be substituted for experience. Additional requirements include the ability to pass the NASA long-duration space flight physical. After the basic selection process, NASA still has many highly qualified individuals. Hence, the process moves to the second step. This involves a week-long process of personal interviews, rigorous medical screening, and orientation, which will result in a reduced list of astronaut candidates. The astronaut candidates undergo a training and evaluation period lasting approximately 2 years. During this time, they will participate in the basic training program, which is designated to develop the knowledge and skills required for formal mission training upon selection. This training is intense. Among other activities, it involves military water survival, scuba certification, spacewalk training, exposure to high and low-pressure environments, and swimming tests. Upon successful completion and positive evaluation, an astronaut candidate becomes an astronaut. Once an astronaut, an individual learns all aspects of on-orbit operations of the International Space Station. Among other activities, astronauts are taught Russian and learn the International Space Station systems, extravehicular activity skills, robotic skills, and aircraft flight readiness. It is also required to have detailed knowledge for each and all experiments of their assigned missions. Training for long-duration missions is even more strenuous and takes an additional 2 to 3 years period. Given all the previous preparation, what do you think? Can astronauts be taught to drill? And who has better chances to be successful when the conditions are the worst possible imaginable? Now that I have made my point, let's pass to the Fermi calculations. First, let me present some quantitative information as reported in the movie. The incoming asteroid has the size of Texas and travels with 22,000 miles per hour. The team of drillers lands on the asteroid when the asteroid reaches the moon, and they need 8 hours to drill a hole 800 feet deep. The nuclear bomb is planted in the hole and detonated exactly at the time barrier to separate the asteroid in 2 fragments, which, we are told, miss Earth by 400 miles. Although the movie refers to Texas for the size of the asteroid, it provides no exact measurements. Hence, we will convert the qualitative statement to a number. The area of Texas is 691,027 square kilometers. If this area is assigned to a square, this would give a length of 831 kilometers for the side of the square. In reality, Texas is stretching 1,244 kilometers from east to west and 1,289 kilometers from north to south. However, this does not modify the order of magnitude of the asteroid size. Both arguments give 1,000 kilometers. Only 16 asteroids have diameters 240 kilometers or greater, and only asteroid Ceres is of the previous size. Ceres has a diameter of 939 kilometers, but it is not in collision course with Earth. There is no extensive literature for the density of the asteroids. Only for some of them, densities have been investigated. For most asteroids, the value of their density is an educated guesswork. The most assumed value is 2,000 kilograms per cubic meter. Therefore, the order of magnitude for the mass of Armageddon's asteroid is 2 times 10 to the power of 21. We will also assume that, after the detonation of a nuclear bomb, the asteroid breaks in 2 fragments of equal mass. This means that each fragment has a mass of 10 to the power of 21 kilograms. Before the detonation, the asteroid is moving towards Earth with a speed of 22,000 miles per hour. We will also assume that the bomb has been planted such that all forces of the explosion appear in the perpendicular direction of the velocity. Therefore, in the forward direction, the fragments continue to move with the same speed. However, after the explosion, they have been given an impulse along the perpendicular direction as desired. Let E stand for the energy delivered by the explosion. To simplify the calculation and also give an advantage to the scriptwriter, our assumption will be that no energy from the nuclear bomb was spent for the splitting of the asteroid to 2 fragments. Then, E is equal to the yield of the bomb. The Hiroshima bomb was equivalent to 13 to 16 kilotons of TNT. Today, a modern nuclear bomb is equivalent to 20 megatons of TNT. The nations with nuclear arsenal do not spend effort to increase the destructive power, as it is already immense. Instead, they focus on reducing the size of the bombs. The script does not provide the magnitude of the yield used in the movie. To be generous, let it be equivalent to 300 times a modern bomb. Given that 1 ton of TNT releases 4.2 times 10 to the power of 9 joules of energy, the released energy is 2 times 10 to the power of 19 joules. And assuming that the energy is distributed evenly among the 2 fragments, each of them receives 10 to the power of 19 joules. This energy becomes kinetic energy along the perpendicular direction. Hence, if v is the speed of the fragments along the perpendicular direction, then kinetic energy equals 1/2 times mass times speed squared, which gives a result for the speed v of 0.14 meters per square second. Finally, we must estimate how long time the fragments travel before they reach Earth. The distance between Earth and the Moon is about 240,000 miles. Hence, once the asteroid has reached the Moon, it will take only 10.9 hours to reach Earth. According to the movie, landing to the asteroid will be attempted at this point, and it will take about 8 hours to drill. Unfortunately, unexpected delays occur during the drilling. It seems quite natural to assume that the detonation will occur about 2 hours before the fatal collision with Earth. However, I will better the odds, and I will assume a lead time of 3 hours or 10,800 seconds. We can now compute the deflection of the fragments by multiplying their speed by the duration of the motion. During this time, each fragment has deflected by a distance of just 1.5 kilometers. Earth's radius is 6,500 kilometers. To this, we may add the thickness of the atmosphere, but it is not really necessary. Comparing Earth's radius with the deflection of the fragments, we understand that NASA's plan is laughable. Instead of a single asteroid collision, NASA creates 2 asteroids which both collide with Earth just 3 kilometers away from each other. Besides the major failure described by the Fermi problem we solved, the movie suffers from many other scientific inaccuracies and errors. I cannot resist the temptation to work out another quick Fermi problem. After landing on the asteroid, the humans walk and behave the exact same way as on Earth. However, this is not possible since the gravitational force has a different value. Have you ever watched NASA's videos on the astronauts trying to walk on Moon, which has acceleration of gravity of 1.62 meters per second square? If not, I have included some original footage for you. If you do not want to see it, skip to 1403. You have now realized that walking on the Moon is hard, and humans need time to get accustomed to it. On the asteroid, the same effect should appear. From Newton's universal law of gravity, the acceleration of gravity of a massive sphere can be expressed in terms of its mass and radius. Then by replacing the mass m in terms of the density rho and the radius, we find that the acceleration of gravity is directly proportional to the density and the radius. Or written another way, using this relation for the Earth and the asteroid, we conclude that on the asteroid, the acceleration of gravity is 0.55 meters per square second. This is very low g, about 3 times smaller than the g on the moon. Walking on the asteroid will be extremely hard. If our drillers can manage it, we can find the pace. To a very basic level, human walking may be approximated as oscillations by a simple pendulum. Then the formula for the period of the oscillations implies larger period on the asteroid, 4.4 times larger than the period on Earth to be exact. Walking on the asteroid must necessarily be very slow. It is more efficient to hop or skip. Even more, the asteroid has highly irregular shape, not spherical as the calculation has assumed. The value of the acceleration of gravity exhibits significant fluctuations from location to location. Therefore, those drillers who travel from a remote location to the location of the drilling should experience this anomaly and be utterly confused and clumsy. And with this, we have concluded today's video. I hope you liked this cinematographic Fermi problem. If you did, please subscribe to my channel to help the creation of more content like this. Thanks a lot for your support.